So, here's something to think about as you settle in tonight. Everything you've ever seen, every star, every streetlight, every face you've ever looked at, every mountain and ocean and cloud, all of it, every single bit of matter you have ever touched or tasted or watched, move across a sky. It makes up roughly 5% of the universe. 5%. That's it. The rest, the overwhelming majority of everything that exists, is something we cannot see, cannot touch, cannot smell, and honestly, can barely even detect. And yet it's there. We know it's there. We've known for decades. We just can't figure out what it is. That's dark matter. And dark energy too. But we'll get to that distinction later. For now, just sit with that number for a moment. 95% of the universe is made of stuff we don't understand. And the roughly 27% of that which we call dark matter, it's not dark because it's far away or dim or hiding behind something. It's dark because it doesn't interact with light at all. Light passes right through it. Or rather, it passes right through light. It doesn't glow. It doesn't reflect. It doesn't cast a shadow. By every measure we use to observe the cosmos, telescopes, cameras, spectroscopes, your own eyes on a clear night, dark matter is completely invisible. And yet, it shapes everything. It holds galaxies together. It bends the path of light across billions of light years. It determined the large-scale structure of the entire universe. Without it, you wouldn't be here. The Earth wouldn't be here. The Milky Way wouldn't exist in any form you'd recognize. And here's the thing. We didn't figure this out all at once. There was no single eureka moment, no lone genius scribbling on a chalkboard who suddenly announced that most of the universe was missing. It was slow. It was messy. It involved decades of data that didn't make sense, astronomers arguing with each other, results that got ignored or forgotten, and a few stubborn people who kept insisting that something was deeply, fundamentally wrong with our picture of the cosmos. The story of dark matter is really a story about what happens when the universe refuses to behave the way you expect it to, and what scientists do when the numbers just won't add up. So, let's go back. Way back. Let's start where this all quietly began, in the early 20th century, when our understanding of the universe was still remarkably small. In the 1920s and 30s, most astronomers thought the Milky Way was basically the entire universe. That's it. One big collection of stars, surrounded by nothing, presumably. The idea that there were other galaxies out there, other island universes as they were sometimes called, was still being debated. Edwin Hubble hadn't yet made his famous observations showing that the Andromeda Nebula was actually a separate galaxy, millions of light years away. The scale of the cosmos was, to most people, still manageable, still comprehensible. But even in this era, before we understood how vast everything really was, a few people started noticing something odd. And the first person who really put numbers to it, the first person to look at the data and say, out loud, that there was far more matter out there than we could account for, was a Swiss astronomer named Fritz Zwicky. Now, Zwicky is one of the most fascinating and underappreciated figures in the history of science, and honestly, part of the reason he's underappreciated is that he was, by most accounts, incredibly difficult to work with. He was brilliant, genuinely, staggeringly brilliant. He worked at Caltech. He coined the term supernova. He predicted neutron stars before they were observed. He contributed to jet engine development during World War II. And he was one of the first people to seriously catalog galaxy clusters. But he was also combative, abrasive, and had a habit of calling his colleagues spherical bastards. His reasoning being that they were bastards no matter which direction you looked at them from. This did not win him many friends. And it may be one reason his most important discovery took decades to be taken seriously. In 1933, Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies about 320 million light-years from Earth. He was trying to figure out how fast the galaxies within the cluster were moving. And this is a pretty standard thing to do. You look at a gravitationally bound system. You measure how fast the objects inside it are moving, and from that, you can estimate how much total mass the system contains. It's the same basic principle you'd use if you watched a ball on a string being swung in a circle. The faster it goes, the more force is needed to keep it on that path, and that force tells you something about the system. In the case of a galaxy cluster, the force holding everything together is gravity, and gravity depends on mass. So if you know how fast the galaxies are moving, you can work backward to figure out how much mass must be there to keep them from flying apart. Zwicky did exactly this. He used something called the virial theorem, which is a formalized way of relating the kinetic energy of objects in a system to the gravitational potential energy holding them together. And when he crunched the numbers, he found something deeply strange. The galaxies in the Coma Cluster were moving way too fast, far faster than they should have been, given the amount of visible matter he could observe. It wasn't a small discrepancy either. The galaxies were moving as if the cluster contained roughly 400 times more mass than what you could see. 400 times. Think about that for a second. It's as if you watched a merry-go-round spinning so fast that the horses should be flying off into the parking lot, and yet they weren't. Something was holding them in place, something massive and invisible. Zwicky called this missing mass Dunklem Materiae, dark matter in German, and he published his findings. And then, largely, the scientific community shrugged. Part of it was Zwicky's personality. People didn't love working with him or engaging with his ideas. Part of it was that the measurements were rough, the techniques were new, and there were plenty of reasons to think maybe the observations were just off. Maybe he'd miscounted the galaxies. Maybe the velocities were wrong. Maybe the virial theorem didn't apply cleanly to something as messy as a galaxy cluster. There were enough escape hatches that most astronomers simply didn't worry about it too much. And so the idea sat there. For decades. This is one of those moments in the history of science that's a little heartbreaking in retrospect, because Zwicky was right. He was right in 1933, but the world wasn't ready to hear it, and he wasn't the kind of person who made it easy for others to listen. Now, here's what's important to understand about why this problem was so easy to ignore. In the 1930s, our tools for observing the universe were still fairly crude. Telescopes were getting better, but spectroscopy, the technique of splitting light into its component wavelengths to measure things like velocity and composition, was still being refined for extragalactic work. The uncertainties in Zwicky's measurements were large, and the theoretical framework for understanding galaxy clusters was still being developed, so it wasn't unreasonable for scientists to think that the discrepancy would go away as better data came in. That's actually a pretty healthy scientific instinct. Don't panic over one anomalous result. Wait for confirmation. But the anomaly didn't go away. It kept showing up. A couple of years after Zwicky's work, in 1936 and 1937, a Sinclair Smith at Mount Wilson Observatory found a similar mass discrepancy in the Virgo cluster. Too much motion, not enough visible matter. And then, quietly, other observers started noticing similar things in other systems, but none of it coalesced into a crisis. It was more like a background hum, an unresolved puzzle that people would occasionally mention at conferences and then move on from. Meanwhile, something else was happening that would eventually become central to the dark matter story, though nobody realized it at the time. Astronomers were starting to measure the rotation of individual galaxies, not clusters of galaxies, but single spiral galaxies, like our own Milky Way. And this is where the story really starts to get interesting, because the rotation of a galaxy is one of the cleanest, most elegant ways to weigh it, and the results were going to turn out to be deeply, persistently wrong. Here's how it works. Imagine looking at a spiral galaxy from the side, or at a slight angle, so you can see it rotating. The stars and gas on one side of the galaxy are moving toward you, and the stars and gas on the other side are moving away from you. You can measure this using the Doppler effect, the same principle that makes a siren sound higher pitched when an ambulance is coming toward you and lower pitched when it's moving away. Light works the same way. Light from objects moving toward you gets shifted slightly toward the blue end of the spectrum, and light from objects moving away gets shifted toward the red end. By measuring these shifts at different distances from the center of the galaxy, you can build up what's called a rotation curve, a graph showing how fast things are orbiting at each distance from the galactic center. Now, here's what you'd expect that rotation curve to look like based on everything we know about gravity. Near the center of a galaxy, where most of the visible mass is concentrated, the dense bulge of stars, the bright core, things should be orbiting pretty fast because there's a lot of mass pulling on them. But as you move farther and farther out, past the bright disk, into the sparse outskirts where there are fewer and fewer stars, the orbital velocity should drop off. It should decline, the same way that the outer planets in our solar system orbit more slowly than the inner ones. Neptune crawls along at about 5 kilometers per second, while Mercury zips around at nearly 50. The farther you are from the central mass, the weaker the gravitational pull, and the slower you need to go to maintain your orbit. This is basic Keplerian motion, named after Johannes Kepler, who worked it out for planets 400 years ago. So you'd expect the rotation curve of a galaxy to rise near the center and then fall off at larger distances. A nice, clean decline. And in the 1930s and 40s, a few early measurements of nearby galaxies seemed roughly consistent with this. But the data was sparse, and the measurements were hard. It wasn't until the 1960s, and especially the 1970s, that technology caught up with the question, and astronomers could finally measure rotation curves with real precision, reaching far out into the faint outer regions of galaxies where the answer was hiding. And this is where a woman named Vera Rubin enters the story. And honestly, if there's one person whose name should be synonymous with dark matter, one person who did more than anyone else to force the scientific community to confront the reality that something enormous and invisible was out there, it's Vera Rubin. She didn't have the combative personality of Zwicky. She was, by all accounts, quietly determined, deeply passionate about astronomy, and persistent in a way that changed everything. But her path to that discovery was anything but smooth, and the obstacles she faced tell you as much about the sociology of science as they do about the physics of the universe. Rubin grew up in Washington, D.C., fascinated by the stars from a young age. Her father helped her build a telescope when she was 14. She wanted to study astronomy at college, and she applied to Swarthmore, which had a good program. But when she told her high school physics teacher she'd been accepted, he said, and this is a near direct quote, "As long as you stay away from science, you should do okay." She was the only astronomy major in her graduating class. She applied to graduate school at Princeton, but Princeton's astronomy program didn't admit women. They wouldn't until 1975. So she went to Cornell instead, and then to Georgetown for her PhD, where she studied under George Gamow, one of the great cosmologists of the 20th century. And even there, even with Gamow's support, her early work was met with skepticism and sometimes outright dismissal, not always because of the science, but sometimes simply because of who she was. Her dissertation, completed in 1954, suggested that galaxies weren't distributed randomly in space, but tended to clump together. This was controversial at the time, though it turned out to be absolutely correct. It's now a foundational observation in cosmology. But the reception was cool, and Rubin spent the next several years raising her 4 children while continuing to do research, often in relative obscurity. It wasn't until the late 1960s that she began the work that would make the invisible visible, partnering with an instrument maker named Kent Ford, who had built a remarkably sensitive spectrograph, a device that could measure the Doppler shifts of stars and gas in galaxies with unprecedented precision. Together, Rubin and Ford started systematically measuring the rotation curves of spiral galaxies, and what they found, galaxy after galaxy, was something that made no sense at all. The rotation curves were flat, completely, stubbornly, inexplicably flat. Let me explain why that's such a big deal, because it really is one of those moments in science where a simple graph on a piece of paper quietly rewrites everything we think we know. Remember how we talked about the way planets orbit the sun, Mercury whipping around fast because it's close to all that gravitational pull, and Neptune drifting slowly way out in the cold because the sun's grip is so much weaker at that distance. That's Keplerian motion. It's what you'd expect from any system where most of the mass is concentrated in the center, and galaxies, at least as far as anyone could see through a telescope, looked like they should follow the same pattern. There's this big, bright bulge in the middle, dense with stars, and then the disk spreads out and gets thinner and dimmer as you move toward the edges. So the stars and gas clouds orbiting way out on the fringes of a galaxy. They should be moving slowly, right? They're far from the bulk of the mass. The gravitational pull out there should be weak. Their orbital velocities should drop off. But Rubin and Ford's data said otherwise. Star after star, gas cloud after gas cloud, all the way out to the farthest reaches they could measure, the orbital speeds stayed high. Not just a little higher than expected. They stayed essentially constant. The rotation curve would rise as you moved out from the center, which is normal, and then it would just level off. It wouldn't come back down. It was like driving away from a city and expecting the road to get quieter. But the traffic just stays the same density, no matter how far into the countryside you go. It doesn't make sense unless there's something out there you can't see. More city, hidden in the dark. And the thing is, this wasn't a marginal effect. It wasn't like the speeds were 5 or 10% higher than expected. In many galaxies, the discrepancy implied that the vast majority of the galaxy's mass was completely invisible. We're talking about situations where what you could see, all the stars, all the gas, all the dust, accounted for maybe 10 or 15% of the mass that had to be there to explain the motion. The rest was just missing. Or rather, it was there, doing its gravitational thing, pulling on everything around it, but it wasn't emitting or reflecting any light at all. Rubin and Ford published their first major rotation curve paper in 1970, focusing on the Andromeda Galaxy, which is our nearest large galactic neighbor. That paper was significant, but it was really their work through the mid-1970s when they extended the analysis to dozens of spiral galaxies that made the case undeniable. By 1978, they had rotation curves for something like 60 galaxies, and every single one showed the same pattern. Flat. Stubbornly, beautifully flat. And Rubin, to her enormous credit, didn't shy away from what the data was telling her. She said it plainly. The galaxies contained enormous amounts of dark matter. She used that phrase. The same phrase Zwicky had coined more than 40 years earlier, back when everyone had ignored him. Now here's what I love about this part of the story. Rubin wasn't working in a vacuum, no pun intended. At almost exactly the same time, completely independently, radio astronomers in the Netherlands and Australia were finding the same thing using a totally different technique. See, Rubin and Ford were measuring optical light, the visible glow of stars and ionized gas. But you can also study galaxy rotation using radio waves, specifically the 21-centimeter emission line of neutral hydrogen. Hydrogen is the most abundant element in the universe, and even in the outer parts of galaxies where there aren't many stars, there's still a lot of cold hydrogen gas floating around. That gas emits radio waves at a very specific frequency, and you can use the Doppler shift of that radio signal to measure how fast it's moving, just like Rubin was doing with visible light, but reaching much farther out into the galaxy's outskirts. Albert Bosma, a Dutch astronomer working on his PhD thesis in the late 70s at the University of Groningen, produced incredibly detailed radio rotation curves of spiral galaxies that extended way beyond where the visible stars petered out. And guess what he found? Flat curves. The same flat curves. Even out there, in regions where there was essentially no visible matter at all. Something was still exerting gravitational pull, keeping the hydrogen orbiting at high speed. Bosma's thesis, published in 1978, was a landmark piece of work, and it dovetailed perfectly with what Rubin and Ford we're seeing in optical wavelengths. Two completely different methods, different instruments, different parts of the electromagnetic spectrum, and they were telling the same story. Think about what that means for a second. When two independent lines of evidence point to the same conclusion, that's powerful. It's much harder to argue that there's some systematic error or some weird instrumental artifact when the result keeps showing up, no matter how you look at it. And this is on top of Zwicky's cluster observations from the 30s, which were a completely different kind of measurement at a completely different scale. Galaxy clusters, individual galaxies, optical light, radio waves, everything was saying the same thing. There is far more mass out there than we can see. But of course, the scientific community doesn't just roll over and accept a radical new idea, even when the evidence is strong. And honestly, that's how it should work. Extraordinary claims require extraordinary scrutiny. So people pushed back. They asked reasonable questions. Could the mass be in the form of ordinary matter that just happens to be dark? Things like dead stars, brown dwarfs, planets, cold gas clouds, black holes, objects made of regular atoms that simply aren't luminous enough to see? This is actually a really important question, and it deserves a careful answer because it gets at the heart of what makes dark matter so strange. These hypothetical objects, ordinary matter hiding in dim or invisible forms, were given a wonderful acronym, MACHOs, Massive Astrophysical Compact Halo Objects. And yes, that name was chosen at least partly as a joke, because the competing theoretical explanation involved particles called WIMPs, weakly interacting massive particles, MACHOs versus WIMPs. Physicists have a sense of humor, even if it doesn't always land. The macho idea is intuitive and appealing. Maybe galaxies are just surrounded by enormous numbers of dim objects, failed stars, rogue planets, ancient white dwarfs that have cooled to the point where they barely glow. These things would be made of perfectly normal matter, protons and neutrons and electrons, what physicists call baryonic matter. They'd be hard to detect because they're faint, but they'd still have mass and they'd still exert gravity. Problem solved, right? Well, not quite. And the reason we know it's not quite comes from one of the most beautiful and precise measurements in all of cosmology: Big Bang nucleosynthesis. Here's the idea. In the first few minutes after the Big Bang, the universe was unimaginably hot and dense, so hot that protons and neutrons were slamming into each other and fusing together, forming the lightest elements: hydrogen, helium, and tiny traces of lithium and deuterium. The exact proportions of these elements that got produced depend very sensitively on one number: the total density of baryonic matter in the universe. If there were more protons and neutrons, you'd get more helium and less deuterium. If there were fewer, you'd get less helium and more deuterium. And here's the beautiful part. We can actually go out and measure the primordial abundances of these elements. We can look at very old, very pristine gas clouds that haven't been contaminated by later generations of stellar fusion, and we can measure how much deuterium and helium they contain. When you do that calculation, when you match the observed element abundances to the predictions of nucleosynthesis theory, you get a number for the total amount of baryonic matter in the universe. And that number is about 4 to 5% of the total energy density of the universe. That's it. All the protons, all the neutrons, all the atoms of every kind, everything that makes up stars and planets and people and gas clouds. It's roughly 5%, but the rotation curves and the cluster dynamics are telling us that the total matter content is more like 25 to 30%. So even if every single baryon in the universe were hiding in some dim, invisible form, even if you took all the ordinary matter and made it as dark as possible, you'd still only account for a fraction of what's needed. The math doesn't work. Most of the dark matter can't be made of ordinary atoms. That's a profound realization. It means we're not just talking about stuff that's hard to see. We're talking about stuff that's fundamentally different from everything we've ever touched, tasted, or built anything out of. It's not atoms. It's not on the periodic table. It's something else entirely. And there were experiments to test the macho hypothesis directly, which is satisfying because science at its best doesn't just argue theoretically. It goes out and looks. In the 1990s, several teams set up clever observing programs to search for machos using gravitational microlensing. The idea is gorgeous in its simplicity. If a massive but invisible object passes between us and a distant star, its gravity will bend the light from that background star, briefly making it appear brighter. It's a tiny, temporary magnification effect predicted by Einstein's general relativity. You can't see the macho itself, but you can see the brightening of the star behind it. Teams including the Macho Project, which monitored millions of stars in the Large Magellanic Cloud, and the EROS collaboration in France, spent years watching and waiting for these telltale flickers. They found some. A handful of microlensing events that suggested there were indeed some compact objects in the halo of our galaxy, but nowhere near enough. The results, published through the late 90s and into the 2000s, conclusively showed that machos could account for at most a small fraction of the Milky Way's dark matter halo. Maybe 10 or 20% at the very most, and probably much less. The rest had to be something non-baryonic, something that doesn't interact with light, something we'd never encountered in a laboratory. So, by the turn of the millennium, the scientific picture was becoming remarkably clear and remarkably strange at the same time. Multiple independent lines of evidence, galaxy rotation curves, galaxy cluster dynamics, Big Bang nucleosynthesis, gravitational lensing surveys, all pointed to the same conclusion. The universe is full of matter that isn't made of atoms, doesn't emit or absorb light, and interacts with ordinary matter primarily through gravity. And the amount of it is staggering. For every kilogram of normal matter in the universe, there are roughly 5 kilograms of this dark stuff. Now, you might be wondering, if dark matter doesn't interact with light, how would we ever detect it directly? How do you catch something that passes right through ordinary matter like a ghost through a wall? And this is where the story takes a turn from astronomy into particle physics. Because starting in the 1980s, theorists began asking a very specific question. What kind of particle could dark matter actually be? And the answer they kept circling back to was something genuinely elegant. See, in the late 70s and early 80s, particle physicists were on an incredible roll. The standard model of particle physics was coming together beautifully. Quarks, leptons, gauge bosons, the whole framework that describes how the fundamental building blocks of matter interact through the electromagnetic force, the weak nuclear force, and the strong nuclear force. It was one of the great intellectual achievements of the 20th century. But even as the standard model was being confirmed, experiment after experiment, theorists knew it couldn't be the whole story. There were too many loose ends, too many parameters that had to be put in by hand, too many coincidences that seemed to demand a deeper explanation. One of the most promising extensions was something called supersymmetry. The idea, in broad strokes, is that every particle we know about has a heavier partner particle, a shadow twin, if you will. For every quark, there's a squark. For every electron, a selectron. For every photon, a photino. I know, the naming convention is a little whimsical, but the physics behind it is serious. Supersymmetry was attractive for all sorts of reasons that had nothing to do with dark matter. It helped solve certain mathematical problems in the standard model. It offered a pathway toward unifying the fundamental forces, and it made the Higgs boson mass more natural. But here's the thing that got everyone excited. Many versions of supersymmetry naturally predicted the existence of a stable, electrically neutral, massive particle that would interact only weakly with ordinary matter. A particle that, if it existed, would have been produced in enormous quantities in the hot early universe and would still be floating around today, invisible, gravitationally influential, and almost impossible to detect directly. This hypothetical particle became known as a WIMP, a weakly interacting massive particle. And the name really does tell you everything you need to know. Massive, meaning it has significant mass, probably somewhere between 10 and 1,000 times the mass of a proton. Weakly interacting, meaning it participates in the weak nuclear force, the same force responsible for certain types of radioactive decay, but not in electromagnetism or the strong force. So it doesn't emit light. It doesn't absorb light. It doesn't clump together into atoms or molecules. It just drifts, passing through ordinary matter almost entirely unimpeded. Now, here's where it gets really beautiful. And this is something called the WIMP miracle. When physicists calculated how many of these particles would have been produced in the Big Bang and how many would survive to the present day, they found something remarkable. If you take a particle with roughly the mass and interaction strength that supersymmetry predicted, not tuned, not adjusted, just the values that fell naturally out of the theory, the abundance of those particles today would be almost exactly the right amount to account for the observed dark matter, density of the universe. The numbers just worked out. You start with well-motivated particle physics, you do a straightforward cosmological calculation, and you land right on the target. That's the WIMP miracle. It felt like more than a coincidence. It felt like the universe was trying to tell us something. And so, beginning in the mid-1980s, experimentalists started thinking seriously about how to actually detect a WIMP. And this is where the engineering challenges become absolutely extraordinary. Because think about what you're trying to do. You're trying to detect a particle that almost never interacts with anything. A WIMP could pass through a light year of solid lead and have only a modest chance of bumping into a single atom. The Earth is being bombarded by a constant wind of these particles. If they exist, billions of them streaming through every square meter of the planet every second, passing through you right now as you lie there and you feel nothing. So how on earth do you build a detector sensitive enough to catch one? The basic idea is conceptually simple, but technically insane. You take a very large, very pure target, a tank of liquid xenon, say, or a crystal of germanium or silicon, and you cool it down. Shield it from every possible source of background noise, and then you wait. If a WIMP happens to collide with one of the atomic nuclei in your target, it will transfer a tiny amount of energy. We're talking about the energy equivalent of a mosquito landing, but at the scale of a single atom. That collision would cause the nucleus to recoil, and depending on your detector technology, that recoil might produce a tiny flash of light, a small amount of heat, or a faint electrical signal. Your job is to detect that whisper of energy and distinguish it from every other possible source of noise. And the noise is the real enemy here. Cosmic rays are constantly raining down from space, smashing into atoms and creating showers of secondary particles. Radioactive decay in the rocks around you, in the walls of your lab, in the materials of your detector itself, even in the bodies of the people operating the experiment. All of it produces signals that look almost exactly like what a WIMP collision would look like. So the first thing you do is go underground. Deep underground. Because hundreds of meters of rock above your head acts as a natural shield, filtering out the vast majority of cosmic rays. This is why some of the most important experiments in the search for dark matter are located in some of the strangest laboratories on Earth. The Gran Sasso National Laboratory in Italy sits beneath the Apennine Mountains, accessed through a highway tunnel with about 1,400 meters of rock overhead. The Sanford Underground Research Facility in South Dakota occupies the former Homestake Gold Mine. The same mine, actually, where Ray Davis conducted his famous solar neutrino experiments in the 1960s. The Bulby Underground Laboratory in England sits in a working potash mine more than a kilometer deep. The Stawell Underground Physics Laboratory in Australia, the Snow Lab facility in Canada, 2 kilometers down in an active nickel mine in Sudbury, Ontario. These are real places where real physicists commute to work by descending in mine elevators, sometimes for 20 minutes at a stretch, into the deep earth. But going underground isn't enough. You also have to obsessively control the radioactive purity of everything in and around your detector. The steel, the copper, the glass, the solder, the cables. Every component has to be screened for trace amounts of uranium, thorium, potassium, 40, radon. Some experiments use copper that was mined and smelted before the era of atmospheric nuclear testing, because modern copper can contain trace amounts of cobalt-60 produced by neutron activation from bomb fallout. Ancient Roman lead, salvaged from 2,000-year-old shipwrecks on the Mediterranean seafloor, has been used as shielding material because it's had millennia for its radioactive contaminants to decay away. Think about that for a second. Scientists in the 21st century are using lead ballast from Roman galleys to search for particles that were created in the first moments after the Big Bang. There's something almost poetic about it. The first generation of direct detection experiments began in the late 1980s and early 90s, and they were modest by today's standards. Small detectors, limited sensitivity, but they established the techniques and proved the concept. One of the pioneering efforts was the work of a group at Stanford led by Blas Cabrera and collaborators using cryogenic detectors cooled to millikelvin temperatures, just a fraction of a degree above absolute zero, where the thermal energy in the detector is so low that even the tiniest energy deposit from a nuclear recoil becomes measurable. Another early effort was the DAMA experiment at Gran Sasso, which took a different approach. Rather than trying to detect individual WIMP collisions, DAMA looked for an annual modulation, a seasonal variation in the dark matter signal caused by the Earth's motion around the Sun. Here's the logic behind that, and it's clever. The Sun is moving through the Milky Way's dark matter halo at a couple hundred kilometers per second. The Earth orbits the Sun at about 30 kilometers per second. So in June, when the Earth's orbital velocity adds to the Sun's velocity through the halo, we're moving faster through the dark matter wind, and you'd expect slightly more WIMP collisions. In December, when the Earth's orbital velocity subtracts from the Sun's velocity, we're moving slower, and you'd expect slightly fewer. The difference is small, maybe a few %, but if you have enough data over enough years, you should be able to see it. And DAMA claimed they did see it, starting with their initial results in the late 90s and continuing with the upgraded DAMA/Libra experiment. The collaboration reported a clear annual modulation signal with exactly the right phase, peaking in early June, bottoming out in December, with statistical significance that grew to extraordinary levels over more than a decade of data. By the 2010s, they were reporting a signal at something like 12 or 13 sigma, which, in particle physics terms, is absurdly significant. A 5 sigma result is considered the gold standard for a discovery. 12 sigma should be case closed. But here's where it gets complicated and, honestly, kind of frustrating. Nobody else could reproduce it. Experiment after experiment, xenon, LAX, CDMS, PandaX, Super CDMS, using different target materials and different detection techniques, searched the same parameter space where DAMA's signal should live and found nothing. Absolutely nothing. The constraints from these other experiments were so tight that a standard WIMP interpretation of DAMA's signal seemed to be ruled out. And yet DAMA kept seeing their modulation year after year with unwavering consistency. This created one of the most contentious debates in modern physics. Was DAMA seeing something real but exotic, something that only shows up in sodium iodide crystals and not in xenon or germanium? Was there some subtle systematic effect, some seasonal variation in the background, muon flux, temperature, radon levels, that was mimicking a dark matter signal? The DAMA collaboration insisted their analysis was sound and refused to share their raw data, which did not help their case in the court of scientific opinion. Other groups, notably the NICE experiment in Spain and the Cozine 100 experiment in South Korea, built detectors using the same sodium iodide crystal technology to try to independently test DAMA's claim. The results from those experiments have been coming in over the last several years, and they've been largely inconsistent with DAMA's signal, though the picture is still not completely settled. It's a messy story, and I bring it up because it illustrates something important about how science actually works at the frontier. It's not clean. It's not always a straight march from hypothesis to confirmation. Sometimes you get results that don't fit, that resist easy explanation, that divide the community for decades. And the stakes are high. If Dama were right, it would be the first direct detection of dark matter, one of the most important discoveries in the history of physics. If they're wrong, well, a lot of careers and resources went into chasing a phantom. Meanwhile, the mainstream direct detection experiments kept getting bigger and more sensitive, driven by a relentless logic. If WIMPs exist and have the properties we think they might, we just need a bigger, cleaner detector to catch one. The progression has been remarkable. The xenon program at Gran Sasso went from xenon 10 with about 15 kilograms of liquid xenon in the mid-2000s to xenon 100 to xenon 1T with 2 metric tons, and now xenon NT with about 8 tons of ultra-pure liquid xenon. The LUX experiment in South Dakota gave way to LIX Zeppelin, or LZ, with 10 tons. PandaX in China's Jinping Underground Laboratory has followed a similar trajectory. Each generation pushes the sensitivity down by roughly an order of magnitude, probing weaker and weaker interaction strengths, and every single one of them has come up empty. No WIMPs. Not one confirmed detection. The parameter space that once looked so promising, the sweet spot predicted by the WIMP miracle, has been steadily carved away. Exclusion limit by exclusion limit. The allowed region where a WIMP could still be hiding has shrunk dramatically. It hasn't vanished entirely. There's still room, especially at lower masses or with certain types of interactions. But the easy version of the WIMP hypothesis, the one that felt so natural and elegant in the 1980s, is under serious pressure. This is a genuinely important moment in the story, because it forces a question that cuts to the heart of how physics works. When your most beautiful theory keeps failing to produce the predicted signal, do you abandon it? Do you modify it? Do you build an even bigger detector and keep looking? And the answer, as it turns out, is all of the above. Because while some physicists doubled down on WIMPs and pushed for next-generation detectors, others began exploring radically different ideas about what dark matter might actually be. And one of those ideas reaches all the way back to a proposal made in 1977 by 2 physicists working on a completely different problem. A problem not about dark matter at all, but about a strange and unexplained symmetry in the strong nuclear force. The particle they predicted was called the axion, and it's one of the most elegant ideas in all of physics. So let me tell you about this, because the origin story of the axion is genuinely wonderful. It starts not with cosmology, not with galaxies spinning too fast, but with quantum chromodynamics, QCD, the theory that describes how quarks and gluons interact inside protons and neutrons. By the mid-1970s, QCD was on solid footing. It explained the strong nuclear force beautifully. But there was this one nagging problem, and it had to do with something called CP symmetry. CP stands for charge parity. Charge symmetry means swapping every particle for its antiparticle. Parity symmetry means flipping everything in a mirror. Left becomes right. Right becomes left. When you combine them, CP symmetry asks, if you swap all particles for antiparticles and also mirror flip everything, do the laws of physics stay the same? Now, the weak nuclear force violates CP symmetry, We've known that since 1964, when James Cronin and Val Fitch discovered it in the decay of neutral kaons. That was a big deal, won them a Nobel Prize. But here's the puzzle. The strong force, described by QCD, has every mathematical reason to violate CP symmetry too. The equations of QCD contain a term, a parameter usually written as theta, that would naturally produce CP violation. And if theta were some random number, which is what you'd naively expect, then the neutron should have a measurable electric dipole moment. Think of it this way. The neutron, even though it has no net electric charge, could have its internal positive and negative charges slightly offset, creating a tiny electric asymmetry. The equations say, this should happen unless theta is extremely close to zero. And when experimentalists went looking for this neutron electric dipole moment, they found nothing. Or more precisely, they found that it's incredibly tiny, at least 10 orders of magnitude smaller than what you'd expect from a random theta value. That means theta, this parameter in QCD, is either exactly zero or absurdly close to zero. And nobody could explain why. There's no obvious reason in the standard model for theta to be zero. It's not protected by any known symmetry. It's just weirdly, suspiciously small. This became known as the strong CP problem, and it bugged a lot of people. Enter Roberto Peche and Helen Quinn. In 1977, working at Stanford, they proposed an extraordinarily clever solution. Instead of just accepting that theta happens to be zero by coincidence, they introduced a new symmetry into the theory. A symmetry that would dynamically drive theta to zero. It's like the difference between balancing a ball on the tip of a needle, which requires incredible fine-tuning, and placing a ball in a bowl where it naturally rolls to the bottom, no matter where you drop it. Pesce and Quinn created the bowl. Their symmetry made theta relax to zero automatically. The strong CP problem just dissolves. But here's the thing about symmetries in particle physics. When you break a continuous symmetry, and the Peche-Quinn symmetry does get broken, you get a new particle. This is a deep result called Goldstone's theorem. And very quickly, in 1978, Steven Weinberg and Frank Wilczek independently realized that the Peche-Quinn mechanism predicted a new, very light particle. Wilczek named it the axion, after a brand of laundry detergent, because it cleaned up the strong CP problem, which is a delightful bit of physics humor, honestly. Now, the original axion that Weinberg and Wilczek described would have been relatively easy to detect. It would have shown up in certain particle decays and beam experiments. People looked for it and didn't find it, which ruled out that first version. But the idea was too good to die. In 1980 and 81, two groups independently proposed what's called the invisible axion, models by Jin Kim on one hand, and by Michael Dine, Willy Fischler, and Mark Schrednicki on the other, along with a related model by Andrei Zitnitsky. These invisible axion models pushed the symmetry-breaking scale much higher, which made the axion much lighter and much more weakly interacting. Harder to detect, yes, but also, and this is the key, potentially produced in enormous quantities in the early universe. And this is where the axion story collides with the dark matter story. Because if axions exist with the right mass, somewhere in the range of micro-electron volts to milli-electron volts, roughly, then the early universe would have produced a vast cold condensate of them, not through thermal processes like WIMPs, but through a completely different mechanism. In the very early universe, as temperatures dropped and the Pexe-Quinn symmetry broke, the axion field would have started oscillating. These oscillations don't behave like hot particles zipping around. They behave like a cold, coherent field, more like a gentle, universe-filling wave than a gas of individual particles. And the energy stored in those oscillations could account for exactly the right amount of dark matter. Think about what that means. You have a particle that was invented to solve a completely unrelated problem in nuclear physics, the strong CP problem, and it turns out, almost as a bonus, to be a perfect dark matter candidate. That kind of convergence, where a solution to one mystery accidentally solves another, is the sort of thing that makes physicists sit up and pay attention. It's not the same as the WIMP miracle, but it has a similar flavor of unexpected rightness. So how do you detect something this ghostly? Axions, if they exist, would be extraordinarily light and interact with ordinary matter even more feebly than neutrinos. But they have one saving grace, one tiny handle you can grab onto. In the presence of a strong magnetic field, an axion can convert into a photon, a real, detectable photon. This was pointed out by Pierre Civicki at the University of Florida in 1983, and it changed everything because it meant you could actually build an experiment to look for axions. Civicki's idea was beautifully simple in concept. You take a large, powerful magnet, the stronger the better, and inside it, you place a microwave cavity, basically a hollow metal cylinder tuned to resonate at a specific frequency. If axions from the dark matter halo surrounding our galaxy drift through that magnetic field, a tiny fraction of them will convert into microwave photons. The frequency of those photons corresponds to the axion's mass. Heavier axions produce higher frequency photons. So you tune your cavity to a specific frequency. Listen for an impossibly faint signal above the noise. And if you hear nothing, you retune slightly and listen again. You're essentially building a radio that's trying to pick up the quietest station in the universe. The flagship experiment based on this idea is called ADMX, the Axion Dark Matter Experiment. It started in the late 1990s at Lawrence Livermore National Laboratory and later moved to the University of Washington in Seattle. A DMX uses a superconducting magnet and a tunable microwave cavity cooled to temperatures just a fraction of a degree above absolute zero, because thermal noise is your enemy when you're listening for signals this faint. Over the years, ADMX has steadily improved its sensitivity, incorporating quantum-limited amplifiers, devices called squids, and later Josephson parametric amplifiers, that push the noise floor down to the fundamental quantum limit. You literally cannot do better without violating the laws of quantum mechanics. And ADMX has started to probe the most theoretically motivated region of axion parameter space. They haven't found a signal yet, but they're now sensitive enough that they're genuinely testing the hypothesis, not just setting limits in less interesting territory. They're scanning through frequencies methodically, like tuning a dial one click at a time. It's painstaking work. Each tiny frequency window requires hours or days of integration to achieve the necessary sensitivity. Scanning the full range of plausible axion masses could take years, even decades. But ADMX isn't alone anymore. A whole ecosystem of axion experiments has sprung up around the world, each targeting different mass ranges or using different detection strategies. Haystack at Yale pushes to higher frequencies, which correspond to higher axion masses, using smaller cavities and even more advanced quantum sensing techniques. Oregon in Australia, CAP in South Korea, the Center for Axion and Precision Physics, which has built an impressive array of magnets and cavities at the Institute for Basic Science in Dijon. These are all chipping away at different parts of the axion mass range. And then there are experiments that don't use cavities at all. Abracadabra, and yes, that's really its name. It stands for a broadband/resonant approach to cosmic axion detection with an amplifying B-field ring apparatus. Takes a completely different approach. Instead of looking for axion to photon conversion in a cavity, it looks for the tiny oscillating magnetic field that a background of axions would generate inside a specially shaped toroidal magnet. CASPER, the cosmic axion spin precession experiment, looks for axions by watching for their effect on nuclear spins, using techniques borrowed from nuclear magnetic resonance, basically MRI technology repurposed to hunt for dark matter. Mad Max in Germany is developing a dielectric haloscope, which uses a stack of ceramic discs inside a magnet to boost the axion to photon conversion signal at higher masses, where traditional cavities become impractically small. What I love about this whole landscape is how creative it is. The axion forces experimentalists to invent entirely new detection concepts, because the particle is so light and so weakly coupled that brute force approaches don't work. You can't just build a bigger tank of xenon. You need cleverness. You need quantum tricks. And the community has risen to the challenge in ways that are genuinely inspiring. There's also a completely different way to look for axions, not from the dark matter halo, but from the sun. The sun should produce axions through interactions in its hot, dense core, and those solar axions could be converted back to X-ray photons in a strong magnetic field here on Earth. This is the idea behind the CAST experiment at CERN, which used a decommissioned Large Hadron Collider test magnet pointed at the sun. CAST ran for years and set strong limits on axion photon coupling, though it didn't find a signal. Its successor, called IAXO, the International Axion Observatory, is being designed as a purpose-built solar axion telescope with much larger magnets and better optics, and it could start taking data in the coming years. Now, I should be honest with you about where things stand. As of right now, no experiment has detected an axion. We don't know if axions exist. We don't know their mass. We don't even know for certain that the strong CP problem requires the Pesce-Quinn solution. Maybe there's some other explanation we haven't thought of. But the theoretical motivation is strong. The experimental program is maturing rapidly. And there's a real sense in the community that if axions are out there in the most natural mass range, we might actually find them within the next decade or two. And here's something worth sitting with for a moment. The axion and the WIMP represent fundamentally different philosophies about what dark matter might be. The WIMP is heavy, tens or hundreds of times the mass of a proton, and interacts through a force we already know about, the weak force. The axion is almost incomprehensibly light, potentially a trillionth the mass of an electron or less, and interacts through an entirely new mechanism tied to the strong force. They're about as different as two dark matter candidates can be. And yet both emerge naturally from attempts to fix known problems in particle physics. Both give you roughly the right amount of dark matter without artificial tuning. Both are testable, at least in principle. But what if it's neither? What if dark matter isn't a WIMP and isn't an axion? This is a question that's gained real traction in the last 15 years or so, as the WIMP searches kept coming up empty, and theorists started exploring the full landscape of possibilities. And that landscape turns out to be vast, almost dizzyingly so. There's a whole category of ideas that goes by the name hidden sector or dark sector models, where dark matter particles interact with each other through forces that we can't feel at all, forces carried by particles we've never seen. Imagine a whole parallel world of physics with its own force carriers, maybe even its own version of atoms and chemistry, overlapping with our universe gravitationally, but otherwise completely invisible. Some of these models predict dark matter that's self-interacting, dark matter particles that bounce off each other. And there are actually some astrophysical observations that might hint at this. Certain discrepancies in the shapes of small galaxies and galaxy clusters that cold, collisionless dark matter has trouble explaining. Then there are sterile neutrinos, hypothetical heavier cousins of the neutrinos we already know about, which would interact with ordinary matter even less than regular neutrinos do. They're fuzzy, dark matter models, where the dark matter particle is so incredibly light that its quantum wavelength stretches across entire galaxies, and the dark matter behaves less like particles and more like a vast, undulating wave. There are primordial black holes, which aren't particles at all, but tiny black holes formed in the first fraction of a second after the Big Bang. And while we've ruled out most mass ranges for these, there are still a few windows where they could potentially account for some or all of the dark matter. The point is, the search has broadened enormously. And this broadening has been accompanied by one of the most remarkable developments in the whole dark matter story. A development that comes not from particle physics at all, but from cosmology, from the study of the oldest light in the universe. Because, while experimentalists were building detectors deep underground and tuning microwave cavities in basements, cosmologists were doing something equally extraordinary. They were mapping the cosmic microwave background with exquisite precision, and what they found would change the dark matter conversation forever. So let's talk about this oldest light. You've probably heard the term before, the cosmic microwave background, or CMB. And we touched on it earlier, but now it's time to really sit with it, because this is one of the most beautiful measurements in all of science, and it tells us things about dark matter that no underground detector or particle collider ever could. Here's the setup. About 380,000 years after the Big Bang, which sounds like a long time, but cosmically speaking, it's the blink of an eye. The universe cooled down enough for the first atoms to form. Before that moment, everything was a hot, dense plasma. Protons and electrons were flying around loose, and photons, particles of light, couldn't travel more than a short distance before slamming into a free electron and scattering off in some random direction. The universe was opaque, like being inside a fog so thick you can't see your hand in front of your face. But then, the temperature dropped below about 3,000 Kelvin, and suddenly, electrons could settle into orbits around protons, forming neutral hydrogen atoms. And once that happened, the photons were free. The fog lifted. Light could travel in straight lines for the first time in the history of the universe, and it's been traveling ever since. That light is still out there. It's been stretched by the expansion of the universe from visible light all the way down into microwaves, which is why we call it the cosmic microwave background. And it's everywhere. It fills the entire sky, coming from every direction. When you tune an old analog television to a channel with no signal, and you see that static, that snow on the screen, a small fraction of that noise is actually CMB photons. You're literally watching the afterglow of the Big Bang. Now, this radiation was first detected accidentally in 1964 by Arno Penzias and Robert Wilson at Bell Labs in New Jersey. They were trying to calibrate a big horn antenna for satellite communications, and they kept picking up this persistent background hiss that they couldn't get rid of. They checked everything. They even cleaned pigeon droppings out of the antenna, thinking that might be the source. It wasn't. The hiss was coming from everywhere in the sky, equally, at a temperature of about 3.5 Kelvin, just a few degrees above absolute zero. They'd stumbled onto the most important cosmological discovery since Hubble showed the universe was expanding. They won the Nobel Prize for it. But here's what matters for our story. The CMB isn't perfectly uniform. It's almost uniform. The temperature is the same in every direction to about 1 part in 100,000. But those tiny, tiny variations, those little hot spots and cold spots, are incredibly important. They're the fingerprints of the early universe. They tell you about the density fluctuations in that primordial plasma, places where matter was slightly more concentrated, and places where it was slightly less. And those fluctuations are the seeds of everything. The slightly denser regions eventually collapsed under gravity to form galaxies and galaxy clusters, and the slightly less dense regions became the great voids of the cosmic web. Everything you see in the universe today, every galaxy, every star, every planet, grew from those tiny temperature variations in the CMB. And here's where it gets really interesting for dark matter. Those density fluctuations weren't just sitting there quietly. They were oscillating. Think of it like sound waves. In the early universe, gravity was pulling matter inward toward the denser regions, compressing it, and radiation pressure was pushing back outward, resisting the compression. So, you got these oscillations, matter falling in, bouncing back, falling in, bouncing back. Acoustic oscillations, literally sound waves rippling through the primordial plasma. And when the universe cooled enough for atoms to form and the photons were released, those oscillations were frozen in place, imprinted on the CMB like a snapshot. Now, here's the thing, and this is really the key insight. Dark matter participates in the gravitational part of this dance, but not the pressure part. Dark matter doesn't interact with photons. It doesn't feel radiation pressure. So while ordinary matter is oscillating back and forth, getting pushed around by light, dark matter just sits there in its gravitational wells, slowly accumulating, providing a gravitational anchor. And this This asymmetry between how dark matter and ordinary matter behave during these acoustic oscillations leaves a very specific, very measurable signature in the pattern of hot and cold spots in the CMB. If you measure the CMB temperature variations across the whole sky and then do a statistical analysis, basically asking, how much variation is there at different angular scales, at different spot sizes, you get what's called the power spectrum. And this power spectrum has a very distinctive shape. It has a series of peaks and troughs, like a mountain range, and the heights and positions of those peaks encode an extraordinary amount of information about the composition of the universe. The position of the first peak tells you about the overall geometry of space, whether the universe is flat, curved like a sphere, or curved like a saddle. The relative heights of the odd and even peaks tell you the ratio of ordinary matter to dark matter. The overall envelope of the peaks tells you the total matter density. It's like a cosmic barcode, and if you can read it precisely enough, you can extract the recipe of the universe. The first really precise measurement of this power spectrum came from a satellite called WMAP, the Wilkinson Microwave Anisotropy Probe, launched by NASA in June 2001. WMAP orbited a point called L2, about 1.5 million kilometers from Earth, where it could stare at the full sky without interference from the sun or the Earth or the moon. And over 9 years of observations, WMAP produced a map of the CMB that was stunningly detailed. The results, first published in 2003 by a team led by Charles Bennett and including David Spergel, Lyman Page, and many others, were a landmark. They confirmed that the universe is geometrically flat. They measured the age of the universe to be about 13.7 billion years. And they measured the composition. Roughly 4% ordinary matter, roughly 23% dark matter, and roughly 73% dark energy. That mysterious stuff we'll get to later. Think about that for a second. Only 4% of the universe is made of the stuff you and I are made of. Everything else is dark. But WMAP was just the beginning. In 2009, the European Space Agency launched Planck, a satellite with even more sensitive detectors, covering a wider range of frequencies with much finer angular resolution. Planck was named after Max Planck, the father of quantum theory, and it lived up to the name. The Planck results, released in stages starting in 2013 and refined through 2018, gave us the most precise measurement of the CMB power spectrum ever made. And the numbers it produced are the ones we use today. The universe, according to Planck, is 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. The age of the universe was refined to 13.8 billion years. And here's what's remarkable. The Planck data fits the theoretical predictions of a universe with cold, dark matter and a cosmological constant, the so-called lambda CDM model, with almost eerie precision. Peak after peak after peak in the power spectrum, the theory and the data line up beautifully. This is worth pausing on because it's one of the strongest pieces of evidence for dark matter that exists, and it comes from a completely different direction than galaxy rotation curves or gravitational lensing or any of the other things we talked about earlier. The CMB is telling us about the universe when it was 380,000 years old, long before any galaxies existed. And it's saying, independently and unambiguously, that there must be about 5 times as much dark matter as ordinary matter. The acoustic peaks wouldn't look the way they do otherwise. If you try to fit the CMB data without dark matter, if you try to explain those peaks using only ordinary matter, you can't do it. The peaks come out wrong. The heights are wrong. The spacings are wrong. Everything is wrong. You need dark matter, and you need it in almost exactly the amount that Zwicky's galaxy clusters and Rubin's rotation curves suggested decades earlier. And there's another piece of the puzzle that fits beautifully here, something called baryon acoustic oscillations, or BAO. Remember those sound waves in the early universe, the ones frozen into the CMB? Well, they were also frozen into the distribution of matter itself. When the universe cooled and the photons decoupled, the sound waves stopped propagating, and they left behind a characteristic scale, a preferred distance at which galaxies are slightly more likely to be found near other galaxies. It's like dropping a stone into a pond, and then freezing the pond. You'd see the ripples preserved in the ice. That preferred distance is about 490 million light-years in today's expanded universe, and it's been measured in galaxy surveys, like the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey. It matches the CMB predictions perfectly. It's the same physics, seen from 2 different angles. One in the oldest light, one in the distribution of galaxies billions of years later. And they agree. So by the mid-2000s, the cosmological case for dark matter was essentially airtight. Multiple independent lines of evidence, rotation curves, galaxy cluster dynamics, gravitational lensing, the CMB power spectrum, baryon acoustic oscillations, the large-scale structure of the cosmic web, Big Bang nucleosynthesis, all converging on the same answer. About 27% of the universe is dark matter. It's cold, meaning it moves slowly compared to light. It's collisionless, or nearly so. It interacts gravitationally, but not electromagnetically. And it's not made of any particle in the Standard Model. Which brings us to a question that might have been nagging at you for a while. If we know so much about what dark matter does, how it shapes galaxies, how it sculpts the cosmic web, how it leaves its fingerprints on the oldest light in the universe, why can't we figure out what it is? Why, after decades of searching, have we never caught a dark matter particle in a detector? And this is where the story takes a turn that some physicists find exhilarating and others find deeply unsettling, because starting around 2010 or so, a different kind of idea began gaining serious traction. An idea that had been lurking in the background for decades, dismissed by most of the mainstream, championed by a stubborn few. The idea that maybe, just maybe, we don't need dark matter at all. That maybe what we're seeing isn't evidence of invisible matter, but evidence that our understanding of gravity itself is incomplete. That gravity, as we understand it through Einstein's general relativity, works beautifully in most situations, but might need a correction, a tweak, a modification. At the scales where we keep invoking dark matter to explain what we see. Now, this idea has a name, and it's been around a lot longer than you might think. It's called MOND, Modified Newtonian Dynamics, and it was proposed in 1983 by by an Israeli physicist named Mordechai Milgram. Milgram was working at the Weizmann Institute of Science in Rehovot, and he'd been staring at those galaxy rotation curves, the same ones Vera Rubin had made famous. And he noticed something peculiar, something that the dark matter explanation didn't naturally account for. See, if every galaxy has its own unique halo of dark matter, you'd expect a lot of variation in how rotation curves behave. Different galaxies, different amounts of dark matter, different distributions. But that's not what the data showed. There was a pattern, a surprisingly tight, clean relationship between how much visible matter a galaxy contained and how fast its outer stars were rotating. It was almost too neat. Milgram realized he could reproduce the flat rotation curves, all of them, across a huge range of galaxy types and sizes, with a single, simple modification to Newton's law of gravity. Here's the idea. Newton tells us that the gravitational acceleration an object feels drops off with the square of the distance. Double the distance, quarter the force. That works fantastically well in the solar system, in laboratories, everywhere we've tested it directly. But Milgram proposed that below a certain very tiny acceleration threshold, around 1/10,000,000th of a meter per second squared, which is absurdly small compared to anything you'd experience on Earth, gravity stops falling off as quickly. Instead of dropping with the square of the distance, it drops more slowly. The effect is subtle, almost non-existent in strong gravitational fields, but in the outer reaches of galaxies, where gravitational accelerations are incredibly weak, it adds up. Stars feel a bit more pull than Newton would predict, so they orbit faster than expected. No dark matter needed. And here's what made people pay attention. Even reluctantly, it worked. Not approximately. It worked with startling precision across an enormous range of galaxies. Milgram's formula, with just one new fundamental constant, that acceleration threshold, called a naught or a zero, could predict the rotation curve of a galaxy if you told it nothing more than the distribution of visible matter. No free parameters for dark matter halo shape, no fitting, no tweaking. Just the visible stars and gas plugged into his modified formula, and out came the right answer. This relationship eventually got formalized into something called the baryonic-Tully-Fisher relation, and it's one of the tightest empirical correlations in all of extragalactic astronomy. The total baryonic mass of a galaxy, stars plus gas, is related to the fourth power of its flat rotation velocity. Dark matter models can accommodate this relationship, but they don't predict it naturally. You have to arrange the dark matter halos just so, in a way that seems almost conspiratorial, to reproduce something that Mond gives you for free. So why wasn't everyone immediately convinced? Well, because galaxies aren't the whole story, and this is where Mond runs into serious trouble. Remember the bullet cluster? That spectacular collision where the visible matter, the hot gas, got separated from where the gravitational lensing says most of the mass is? In a Mond universe without dark matter, the gravity should follow the visible matter. But it doesn't. The lensing maps clearly show mass concentrations offset from the gas, sitting right where the galaxies are, exactly as you'd expect if invisible dark matter halos passed through each other while the gas got stuck. Mond, at least in its original form, doesn't have a clean explanation for this. It's a real problem, And then there's the CMB. All those beautiful acoustic peaks we talked about, the precise pattern of hot and cold spots in the cosmic microwave background. Dark matter's role as a gravitational scaffold that doesn't oscillate with the baryons is baked into the physics of how those peaks form. MOND, in its simplest version, doesn't give you that scaffolding. Without dark matter, the predicted CMB power spectrum looks wrong. The peaks are in the wrong places, with the wrong relative heights. Now, Milgram and his supporters knew about these problems, and they weren't idle. In 2004, a physicist named Jacob Bekenstein, famous for his work on black hole thermodynamics, constructed a fully relativistic version of MOND called TVES, for tensor vector scalar gravity. This was a big deal, because it meant MOND wasn't just a phenomenological recipe anymore. It was embedded in a proper relativistic framework that could, in principle, handle gravitational lensing and cosmology. TVES could reproduce some of the lensing observations and made progress on the CMB, though it never quite matched the precision of lambda CDM. But here's where the story gets really interesting, and honestly, a bit poignant. In 2017, something happened that many people thought would be the death blow for modified gravity theories. 2 neutron stars spiraled into each other about 130 million light-years away in an event called GW 170817. The LIGO and Virgo gravitational wave detectors picked up the signal, and just 1.7 seconds later, the Fermi Space Telescope detected a burst of gamma rays from the same location. Think about what that means. Gravitational waves and light traveling across 130 million light-years of space arrived within less than 2 seconds of each other. That tells you that gravitational waves travel at the speed of light to extraordinary precision. The difference is less than a few parts in a quadrillion. Why does this matter for modified gravity? Because many of these alternative theories, including TVES, predicted that gravitational waves should travel at a different speed than light. The extra fields in the theory, the vector fields, the scalar fields, would cause gravitational waves to propagate slightly faster or slower, and GW 170817 ruled that out definitively. Within weeks of that observation, several modified gravity theories were effectively eliminated. TVES, in its original form, was one of them. You might think that would be the end of the story. MOND had its moment. It made some impressive predictions for galaxies, but it couldn't handle the full range of cosmological evidence, and the neutron-star merger sealed the deal. Case closed. Dark matter wins. But science is rarely that clean, and the people working on modified gravity are not cranks. They're serious physicists who keep pointing to something genuinely puzzling, that tight correlation between visible matter and gravitational acceleration in galaxies. In 2016, a team led by Stacy McGaugh, Federico Lelli, and Jim Schumbert published a landmark paper analyzing 153 galaxies from the SPARC database that stands for Spitzer Photometry and Accurate Rotation Curves, and they found that the relationship between the observed gravitational acceleration and the acceleration predicted from visible matter alone was astonishingly tight. Scatter in the data was tiny, consistent with observational uncertainties. It was as if the dark matter somehow knew exactly how much visible matter was present and arranged itself accordingly. This is called the radial acceleration relation, and it's a genuine puzzle for the standard dark matter picture. If dark matter is a separate substance with its own complex dynamics, why should there be such a clean, universal relationship between what the dark matter does and what the visible matter does? In MOND, this relationship is built in by construction. In lambda CDM, it has to emerge from the complicated physics of galaxy formation, gas cooling, star formation, supernova feedback, all conspiring to produce this tight correlation. Some simulations have managed to reproduce it, but the debate over whether they do so naturally or only with careful tuning is still very much alive. And since 2017, new versions of modified gravity have appeared that survive the gravitational wave speed constraint. Theories that modify gravity in ways that only show up at cosmological scales or at very low accelerations, without affecting how gravitational waves propagate. The field is smaller and more constrained than it was, but it's not dead. So where does this leave us? The honest answer, and this is something that the best scientists on both sides will tell you, is that we're in a genuinely strange situation. The cosmological evidence for dark matter is overwhelming. The CMB, the large-scale structure, the bullet cluster, nucleosynthesis, all of it points to a universe where about 27% of the energy density is in some form of cold, non-baryonic matter. But at the scale of individual galaxies, there are patterns and regularities that dark matter models struggle to explain naturally, patterns that MOND captures with almost eerie precision. Some physicists think this means there really is dark matter, but it has properties we haven't fully appreciated yet. Maybe it interacts with itself in ways that produce these galactic regularities. Others think MOND is capturing a deep truth about gravity that we don't yet understand, and that the cosmological evidence attributed to dark matter might eventually find a different explanation. And a growing number of researchers suspect the answer might involve elements of both, that our theory of gravity might need modification, and there might be dark matter. And the full picture requires something we haven't thought of yet. This uncertainty, by the way, is not a failure of science. It's science working exactly as it should. Multiple hypotheses being tested against increasingly precise data, with the answer not yet clear. And the data keeps getting better. New surveys, new telescopes, new experiments are coming online right now that will push both dark matter models and modified gravity theories harder than ever before. Which brings us to what's happening right now, in the present moment, in labs and observatories around the world. Because the search for dark matter hasn't slowed down. If anything, it's accelerating. And the tools being deployed are unlike anything previous generations of physicists could have imagined. There's a new generation of direct detection experiments that makes the xenon detectors we talked about earlier look almost quaint by comparison. The biggest of these is called LZ, short for LX Zeppelin, and it sits nearly a mile underground in the Sanford Underground Research Facility in Lead, South Dakota. The same old Homestake gold mine where Ray Davis set up his famous neutrino experiment back in the 1960s. There's something poetic about that. The same hole in the ground that helped reveal one mystery about invisible particles is now being used to hunt for a completely different kind of invisible particle decades later. LZ came online in 2022, and it's a beast. The heart of it is a tank containing 10 metric tons of ultra-purified liquid xenon. 10 tons. When we talked about those earlier xenon experiments, the ones that kept setting tighter and tighter limits on WIMP interactions, those were working with maybe 1 or 2 tons of xenon at most. LZ scaled that up dramatically, and in particle physics, scale matters enormously. The logic is straightforward. If dark matter particles interact with normal matter incredibly rarely, then the more normal matter you put in front of them, the better your odds of catching one of those rare interactions. It's like trying to catch a specific raindrop. You can hold out a teacup, or you can hold out a swimming pool. LZ chose the swimming pool. And here's what's really impressive about this experiment. The xenon has to be unbelievably pure. Any trace of radioactive contamination, and we're talking about levels so tiny they're measured in parts per trillion, would create background signals that could mimic or drown out a genuine dark matter interaction. The team spent years developing purification techniques to strip out contaminants, like krypton-85 and radon. The xenon in LZ is some of the purest material ever assembled by humans. That's not an exaggeration. The level of purity required is staggering when you think about it, because you're trying to detect events where a single particle nudges a single xenon nucleus, producing a tiny flash of light and a handful of electrons. That's your signal, and you need to be absolutely certain that nothing else in or around your detector could have produced that same tiny flash. The mile of rock overhead helps with cosmic rays. It filters out most of the high-energy particles raining down from space that would otherwise flood the detector with noise. But the rock isn't enough. The xenon tank itself is surrounded by another tank of purified water, which acts as an additional shield. And then the detector has an inner veto system, an outer veto system, layers upon layers of protection designed to catch and reject anything that isn't a genuine dark matter candidate event. The engineering is extraordinary. It's one of the most sensitive instruments ever built by human beings, sitting in the dark, deep underground, waiting. And what has it found? As of its early science runs, LZ has set the most stringent limits ever on the cross-section for WIMP nucleon interactions, which is a technical way of saying it has looked harder than anyone ever has and still hasn't seen a dark matter particle. The constraints are now pushing into territory that would have seemed almost impossibly sensitive just 15 years ago. For a WIMP with a mass around 36 giga-electron volts, that's roughly 36 times the mass of a proton, LZ has ruled out interaction cross-sections down to about 9.2 times 10 to the minus 48 square centimeters. That number is so small, it's almost meaningless to the human brain. But what it means in practice is that if WIMPs exist with those properties, they interact with normal matter even less frequently than the most optimistic models predicted. Now, running alongside LZ is XENONNT, based at the Gran Sasso National Laboratory in Italy, deep under the Apennine Mountains. Same basic idea, a multi-ton liquid xenon detector, exquisitely shielded, searching for that faint nuclear recoil. XENONT uses about 8.6 tons of xenon and has achieved similarly remarkable sensitivity. And there's Panda X4T in China, operating at the China Jinping Underground Laboratory, which is the deepest underground lab in the world, sitting beneath about 2,400 meters of rock. All three experiments are effectively in a friendly competition, each pushing sensitivity limits, each independently confirming that if WIMPs are out there, They're hiding extremely well. Here's the thing about these null results, though. They're not nothing. They're actually incredibly informative. Every time an experiment looks and doesn't find WIMPs at a certain sensitivity level, it eliminates a whole swath of theoretical parameter space. It tells physicists, okay, dark matter doesn't have these particular properties. Cross that off the list. And what's been crossed off over the past 2 decades is substantial. The simplest, most vanilla WIMP models, the ones that originally motivated the whole search, the ones connected to supersymmetry, many of those are now severely constrained or effectively ruled out. The WIMP miracle, that beautiful numerical coincidence we talked about earlier, where a particle with weak force-scale interactions naturally gives you the right abundance of dark matter. That coincidence is looking less miraculous all the time. Not dead, but definitely on life support. And this is where the field is going through something of an identity shift. For 30 years, the WIMP was the leading candidate, the safe bet, the particle that most physicists would have put their money on. The entire experimental infrastructure, the underground labs, the xenon detectors, the analysis pipelines, was built around finding WIMPs. And as the parameter space shrinks and shrinks and the WIMPs stubbornly refuse to show up, the community is broadening its horizons in a serious way. You can feel this shift in the kinds of experiments being proposed and funded right now. Remember those axion searches we talked about? A DMX at the University of Washington has been steadily improving, scanning through different frequency ranges looking for the faint microwave photons that an axion would produce in a strong magnetic field. They've actually started excluding certain axion mass ranges with real sensitivity, not just setting limits in some abstract theoretical space, but genuinely probing the regions where the most well-motivated axion models predict the particle should be. And there are new axion experiments with wonderfully creative names. Abracadabra, Mad Max, Organ, Casper. Each designed to search for axions in different mass ranges using different detection strategies. The axion search has gone from a niche effort to a major thrust of the field. But it goes beyond just WIMPs and axions. There's a whole zoo of new detection concepts targeting dark matter candidates that would have been considered exotic or fringe just a decade ago. Some experiments are looking for dark matter particles much lighter than traditional WIMPs, particles with masses in the megavolt range, or even lighter, 1,000 times less massive than what xenon detectors are optimized for. At those low masses, a dark matter particle wouldn't have enough momentum to noticeably kick a heavy xenon nucleus. It would be like throwing a ping pong ball at a bowling ball. The bowling ball barely moves. So instead, these experiments use lighter target materials. Some use silicon or germanium crystals cooled to millikelvin temperatures, where even the tiniest energy deposit from a dark matter collision would be detectable as a minuscule rise in temperature. Others are exploring even more exotic targets: superfluid helium, molecular gases, even specially designed materials where a single dark matter interaction could break a chemical bond or flip a magnetic spin. And then there's the approach of looking not underground, but up. Dark matter, if it exists, should be everywhere in the galaxy, including right here in our solar system. But it should be especially concentrated in certain places, the center of the galaxy, for instance, or in dense clumps orbiting within the Milky Way's halo. And if dark matter particles can annihilate with each other, if a dark matter particle meets its antiparticle and they destroy each other, converting their mass into energy, that annihilation should produce detectable signals, gamma rays, neutrinos, positrons, antiprotons. So there are space-based telescopes and ground-based observatories specifically looking for these indirect signatures. The Fermi Gamma Ray Space Telescope, launched in 2008, has been scanning the sky for over 15 years now, and it's found something genuinely intriguing. There's an excess of gamma rays coming from the center of the Milky Way, more gamma rays than you'd expect from known astrophysical sources, and the energy spectrum of this excess is roughly consistent with what you'd predict from dark matter particles annihilating. When this was first reported around 2009 and refined over subsequent years, it generated enormous excitement. Could this be the first indirect detection of dark matter? The signal is real. The excess gamma rays are definitely there, but the interpretation is fiercely debated. It could be dark matter. It could also be a population of thousands of millisecond pulsars, rapidly spinning neutron stars, clustered near the galactic center, each too faint to detect individually, but collectively producing the observed gamma ray glow. Disentangling these possibilities has turned out to be devilishly difficult, and as of now, the question remains open. Meanwhile, the Alpha Magnetic Spectrometer, AMS-02, has been bolted to the outside of the International Space Station since 2011, measuring cosmic rays with unprecedented precision. It's detected an excess of positrons, antimatter electrons, at energies that could be consistent with dark matter annihilation. But again, pulsars could explain it too. This is the frustrating reality of indirect detection. The signals you're looking for can almost always be mimicked by conventional astrophysical sources that are just poorly understood. So where does all of this leave us? We have three main avenues of searching for dark matter: direct detection underground, indirect detection via astrophysical signals, and production at particle colliders like the Large Hadron Collider. And across all three, the story as of right now is the same: tantalizing hints, extraordinary sensitivity, but no definitive discovery. The LHC has searched for dark matter particles in proton-proton collisions at energies up to 13.6 TeV and found nothing beyond the standard model. The underground detectors have reached sensitivities their designers would have considered science fiction. The space telescopes have mapped the gamma-ray sky with exquisite precision, and dark matter remains invisible. But here's what's genuinely exciting. The next decade is going to be transformative regardless of what dark matter turns out to be. The Vera Rubin Observatory in Chile, named after the astronomer whose rotation curve measurements did so much to establish the case for dark matter, is about to begin its legacy survey of space and time. Over 10 years, it will photograph the entire visible southern sky every few nights, building up the most detailed map of the universe's large-scale structure ever created. The gravitational lensing data alone, the subtle distortions in galaxy shapes caused by intervening dark matter, will map the distribution of dark matter across billions of light years with unprecedented resolution. The European Space Agency's Euclid telescope, launched in 2023, is doing complementary work from orbit, surveying billions of galaxies to trace how dark matter's gravitational scaffolding has evolved over cosmic time. And these surveys won't just test whether dark matter exists. That's pretty well established at cosmological scales. They'll test what dark matter does, how it clumps, whether it clumps too much or too little compared to predictions, whether the small-scale problems that have nagged at Lambda CDM for decades, the missing satellites, the cusp core problem, the too big to fail problem, are real discrepancies or just artifacts of incomplete simulations, because the simulations are getting better too. Modern cosmological simulations, like Illustri's TNG and FIRE, can now model galaxy formation with enough resolution to include the messy effects of gas physics, star formation, and supernova feedback alongside dark matter gravity. And as these simulations improve, some of those small-scale problems have started to look less severe. It turns out that when you properly account for the explosive energy that supernovae inject into the gas in small galaxies, the gas gets blown around, and the gravitational potential changes, and the dark matter redistributes itself in ways that soften those sharp central cusps into the flatter cores that observers actually see. Maybe dark matter doesn't need exotic self-interactions after all. Maybe we just needed better simulations. But maybe not. Maybe the regularities that MOND captures, that tight radial acceleration relation, the way galaxy dynamics seem to know about a single acceleration scale, are telling us something profound that better simulations alone won't explain. This is the tension at the heart of modern dark matter research, and it's a productive tension, the kind that drives science forward. The next generation of data is going to squeeze both sides hard. If dark matter is a particle, these experiments and surveys are closing in on it from every direction. And if gravity needs modification, the precision of upcoming measurements will make it increasingly difficult to hide a deviation from general relativity. There's one more frontier worth talking about, one that connects dark matter research to some of the deepest questions in fundamental physics. And that's the connection between dark matter and the nature of the universe itself. Because here's the thing. Dark matter doesn't just sit in some isolated corner of physics, waiting patiently for experimentalists to find it. It connects to almost every deep open question we have. The hierarchy problem, the matter-antimatter asymmetry, the nature of dark energy, the possibility of extra dimensions, the unification of forces. Dark matter is tangled up in all of it, and that's part of what makes this search so compelling and so maddening and so beautiful all at once. Let's start with the one that's maybe most intuitive, the matter-antimatter asymmetry. You exist. I exist. Stars and planets and galaxies exist. They're all made of matter. But the laws of physics, as we understand them, treat matter and antimatter almost identically. When the universe was born in the Big Bang, it should have produced equal amounts of both, and matter and antimatter annihilate each other on contact, converting into pure energy. So, if the universe started with equal parts of each, everything should have annihilated, and we should be left with nothing but a sea of photons, no atoms, no stars, no you. But here we are. Something tipped the balance, ever so slightly, in favor of matter. For every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny surplus, 1 part in 1,000,000,000, is everything you've ever seen or touched or known. And we don't fully understand why that imbalance existed. Now, here's where dark matter enters the picture. Some theories of dark matter are deeply connected to this puzzle. In certain models, the same mechanism that created the matter-antimatter asymmetry also determined how much dark matter exists. These are called asymmetric dark matter models. The idea is elegant. Just as ordinary matter has a slight excess over antimatter, dark matter might also carry an asymmetry. Dark matter particles and dark antimatter particles mostly annihilated in the early universe, and what's left over is the surplus, the asymmetric remainder. And if the asymmetry in the dark sector is linked to the asymmetry in the visible sector, if they were generated by the same process, then you'd naturally expect the amount of dark matter and the amount of ordinary matter to be related. And here's the kicker. They are related. The ratio of dark matter to ordinary matter in the universe is roughly 5 to 1. That's close enough to 1 to 1 that it's suspicious. If dark matter were produced by some completely unrelated mechanism, there's no reason its abundance should be anywhere near the abundance of ordinary matter. It could be 1,000,000 times more or 1,000,000 times less, but it's 5 times more. That's suggestive. It hints that maybe the two abundances have a common origin. Asymmetric dark matter models take that hint seriously, and they predict dark matter particles with masses in the range of a few giga-electron volts, roughly the mass of a proton, which, interestingly, is lighter than the classic WIMP mass range. And that's one of the reasons the field has been pushing hard to develop detectors sensitive to lighter dark matter particles. Those sub-GeV detection efforts we talked about earlier aren't just casting a wider net for the sake of it. They're motivated by real theoretical ideas like this one. Then there's the connection to neutrinos, which is another thread worth pulling on. Neutrinos are the ghosts of the particle physics world. They barely interact with anything. Trillions of them are passing through your body right now, and you'll never notice. For a long time, physicists thought neutrinos were massless, just like photons. But starting in the late 1990s, experiments in Japan and Canada, Super Kamiokande and the Sudbury Neutrino Observatory, proved that neutrinos do have mass, tiny, tiny mass, but not zero. And this was a big deal, because the standard model of particle physics, as originally written, said neutrinos should be massless. The fact that they have mass means the standard model is incomplete. There's new physics hiding in the neutrino sector, and some of the mechanisms that could give neutrinos their tiny masses, particularly something called the seesaw mechanism, naturally produce heavy partner particles. Very heavy, very weakly interacting particles. Some of these could be dark matter candidates. In certain versions of the seesaw mechanism, you get what are called sterile neutrinos. Neutrinos that don't interact through any of the known forces except gravity. They're even more ghostly than regular neutrinos. And a sterile neutrino with a mass of a few kilo electron volts, that's a few thousand electron volts. Much lighter than a WIMP, but much heavier than a regular neutrino. Could be a viable dark matter candidate. It would behave as what physicists call warm dark matter, intermediate between the hot dark matter of regular neutrinos and the cold dark matter of WIMPs. There was actually a tantalizing hint a few years back. Around 2014, a couple of groups reported detecting an unexplained X-ray emission line at an energy of about 3.5 kilo-electron volts coming from galaxy clusters and the Andromeda Galaxy. If a sterile neutrino with a mass of about 7 kilo-electron volts were slowly decaying, it would produce an X-ray photon at exactly that energy. People got excited, but subsequent observations have been mixed. Some telescopes see the line, others don't, and the significance has faded somewhat. It's one of those signals that's right on the edge, tantalizing, but not definitive. The story isn't over, though. Future X-ray observatories with better energy resolution might settle it. And then, zooming out even further, there's the question of dark energy. We've been careful throughout this whole conversation to keep dark matter and dark energy separate, because they really are separate phenomena, as far as we know. Dark matter clumps. It has gravitational attraction. It forms halos around galaxies and holds clusters together. Dark energy does the opposite. It drives the accelerating expansion of the universe, pushing everything apart. Dark matter makes up about 27% of the total energy budget of the universe, and dark energy makes up about 68%. Together, with ordinary matter's 5%, that accounts for everything. But here's a question that keeps some cosmologists up at night. Is it a coincidence that dark matter and dark energy have comparable densities right now? In the early universe, dark matter dominated and dark energy was negligible. In the far future, dark energy will dominate completely and dark matter will be diluted to almost nothing. But right now, in this particular epoch, they're within a factor of a few of each other. This is called the coincidence problem, and it bothers people because there's no obvious reason why we should happen to live in the one era when these two very different components are roughly balanced. Some theorists have proposed models where dark matter and dark energy are actually connected, where they interact with each other, or where they're different manifestations of the same underlying thing. These are speculative ideas, and none has gained wide acceptance, but they illustrate how dark matter research connects to the biggest questions in cosmology. So where does all of this leave us? Let me try to paint the picture, honestly, because I think the honest picture is actually more interesting than a neat, tidy story would be. We know dark matter exists. The evidence is overwhelming and comes from so many independent directions: galaxy rotation curves, galaxy cluster dynamics, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, the formation of galaxies themselves, that you can't reasonably deny it. Something is out there, something massive, something dark, something that doesn't interact with light. The case for that is as strong as almost anything in science, but we don't know what it is. And after decades of searching, the simplest, most popular candidates, the vanilla WIMPs that supersymmetry predicted, the ones that should have shown up in underground detectors or at the Large Hadron Collider by now, they haven't shown up. That doesn't mean WIMPs are dead. There's still parameter space left to explore, and the next generation of experiments will push further. But the easy version of the story, the one where we build a big enough detector and a WIMP obligingly scatters off a xenon nucleus, and we pop champagne, that version has gotten a lot harder to believe. The WIMP miracle is on life support, as we said. It's not dead, but it's in the ICU, and so the field has broadened. Axions are being hunted with resonant cavities and novel electromagnetic designs. Sub-GeV particles are being pursued with entirely new detection technologies. Sterile neutrinos are being searched for in X-ray observations. Primordial black holes haven't been completely ruled out in certain mass windows. Self-interacting dark matter is being tested against observations of galaxy cluster collisions and the inner structure of dwarf galaxies. And modified gravity, while struggling with the bullet cluster and the CMB, still captures patterns in galaxy dynamics that cold dark matter models haven't fully explained from first principles. The field is wider and more creative than it's ever been, and the tools are extraordinary. The Vera Rubin Observatory is about to begin the most ambitious survey of the sky ever attempted, mapping billions of galaxies and using their distorted shapes to trace the invisible scaffolding of dark matter across cosmic time. The Euclid Space Telescope, launched in 2023, is doing complementary work from above the atmosphere, measuring the geometry of the universe with exquisite precision. DSI, the Dark Energy Spectroscopic Instrument, is mapping the three-dimensional positions of tens of millions of galaxies to track how the expansion of the universe has changed over billions of years. On the particle physics side, next-generation detectors like Darwin, now being planned, aim to push the sensitivity of direct detection experiments to the so-called neutrino floor, the point where neutrinos from the sun and cosmic rays become an irreducible background. If WIMPs exist above that floor, Darwin should find them. If they don't show up even there, it will be a strong signal that we need to look in a fundamentally different direction. Think about what that means for a second. We're building instruments sensitive enough to detect the faintest whisper of a particle that might not even exist in the form we're looking for. We're mapping the shapes of galaxies billions of light years away to infer the presence of something we can't see, can't touch, can't bottle. We're running simulations of the entire observable universe on supercomputers, trying to match the cosmic web that dark matter wove over 14 billion years. The sheer ambition of it is staggering, and the humility embedded in it, the acknowledgement that 85% of all the matter in the universe is something we haven't identified. That's not a failure of science. That's science at its most honest. There's a beautiful irony in all of this. Fritz Zwicky, back in 1933, was kind of a difficult person. Brilliant, abrasive, ahead of his time in ways that annoyed his colleagues. He saw something in the coma cluster that didn't add up, and he said so, and people mostly ignored him. Vera Rubin, decades later, faced her own barriers as a woman in a field that didn't always welcome women. And she measured galaxy rotation curves with a quiet, meticulous determination that eventually made the evidence undeniable. Neither of them lived to see the mystery solved. Zwicky died in 1974. Rubin died in 2016. The dark matter problem has now outlived the people who first articulated it. And that's okay. Some questions in science are bigger than any one career, any one generation. The question of what most of the universe is made of, that's one of those questions. And you know what? If you've been drifting in and out through all of this, that's perfectly fine. You don't need to hold every detail in your head. The big picture is simple and worth carrying with you. The universe is mostly invisible. The stuff we're made of, atoms, the elements on the periodic table, everything you've ever seen. That's the minority. The majority is something else, something patient and quiet and everywhere, pulling gently on galaxies, shaping the largest structures in existence, and stubbornly refusing to tell us its name. We're looking for it. We're looking with detectors buried deep underground, with telescopes in space, with particle accelerators, with computer simulations, with mathematics, with creativity and persistence, and the same stubborn curiosity that made Zwicky squint at that cluster of galaxies 90 years ago and say, something's missing. And one day, maybe, someone will find it. Maybe it'll be a graduate student in a lab somewhere, staring at a signal on a screen at 3 a.m, not quite believing what they're seeing. Maybe it'll be a theorist who writes down the right equation, and suddenly, everything clicks. Maybe it'll come from a direction nobody expected. That's how it usually works in science. The biggest discoveries tend to sneak up on you. But for now, the mystery is still open. The universe is still mostly dark. And there's something peaceful about that, if you let it be. You're lying here, in the dark yourself, and all around you, passing through you, through the walls, through the earth beneath you. There might be dark matter particles streaming by, silent and untouchable, part of a vast cosmic web that connects everything. You can't feel them. You'll never feel them. But they're part of the same universe you are, shaped by the same gravity, born in the same Big Bang. Whatever dark matter turns out to be, it's been here all along, holding things together in ways we're only beginning to understand. And that's a good thought to fall asleep to. The universe is vast and strange and mostly unknown, and we're slowly, gently, patiently figuring it out, one galaxy at a time, one photon at a time, one quiet night at a time.